Okay, we want the differential equation governing the inductor current I sub L of t for t greater than 0 for this circuit. We have two energy storage elements, a 0.5 farad capacitor and a 3 Henry inductor. At t equals 0, the switch moves from position A to position B. So for t greater than 0, the switch is in this position. The constant source is connected to the inductor, so the inductor will charge up. Since we need the differential equation for t greater than 0, let's just go ahead and redraw the circuit with the switch in the correct position. This leg won't matter anymore, so it will be missing. So this is the circuit we'll be analyzing. When I do a circuit analysis or write the differential equation for a circuit, I always label capacitor voltages and inductor currents as my unknowns. Then I write on my circuit diagram the current through the capacitor. So this current's going to be 0.5, the capacitance, times dVc by dt. Likewise for the inductor, its voltage is going to be 3 henries times dIL by dt. Now I've got my sign conventions taken care of for the energy storage elements and the voltage current relationships for the energy storage elements. Now I really just need to do KVL, KCL, and Ohm's law. Let me call this node A and do KCL at node A. I have 6 amps going into that node. So the currents into the node have to equal the sum of the currents leaving the node. The current through the capacitor is 0.5 dVc by dt. And the current in this direction, if I do KCL here, the current through the 2 ohm resistor is going to be I sub L of t, so that's I sub L. There's one equation and two unknowns. I need to write another equation. Doing KVL through a current source won't do me any good, so let me do KVL around here. So if I start down here, I see the negative terminal on V sub C first. Then this voltage, if I use I sub L as the current through the 2 ohm resistor, will be 2 ohms times I sub L by Ohm's law, plus the voltage across the inductor, which is 3 dIL by dt. Now I have two equations and two unknowns. I need to eliminate V sub C from those equations. The easiest thing is probably to solve one of them for V sub C, plug that into the other one. So this one's easy to solve for V sub C. V sub C is 2IL plus 3 dIL by dt. I need dVc by dt, so if I differentiate this with respect to time, I get dVc by dt is equal to 2 dIL by dt plus 3d squared IL by dt squared. Now I can plug this in for dVc by dt. Going up here, 6 amps is going to be 0.5 times this mess, 2 dIL by dt plus 3 d squared IL by dt squared plus IL. There's a second order differential equation for I sub L. I can simplify it if I want, but it's a legitimate answer to the question as is. Now let me do initial and final conditions. Initial conditions are almost invariably based on the fact that capacitor voltages can't change instantly and inductor currents can't change instantaneously. So let's look at the circuit at t equals 0 minus just before the switch has moved from position A to position B. Now, if this switch has been in this position for a long time, the forcing function is constant, so everything will become constant and the capacitor will look like an open circuit, so there will be no current through the capacitor. And the inductor will look like a short circuit, so there will be no voltage across the inductor. Now if I do KCL here, there's no current through the capacitor, so I have 6 amps going through the 2 ohm resistor. KVL around here tells me that this voltage is going to be the same as this voltage. So V sub C at t equals 0 minus is by Ohm's law just 6 amps times 2 ohms, which is 12 volts. There is no forcing function connected to the inductor, so I sub L at 0 minus, the inductor initially doesn't have any energy stored in it, so this is 0 amps. The initial conditions are at t equals 0 plus just after the switch moves, so V sub C at 0 plus. Now I invoke the idea that capacitor voltages can't change instantaneously. That's equal to V sub C at 0 minus, and that's 12 volts. Likewise, inductor currents can't change instantaneously, so I sub L at 0 plus is the same as I sub L at 0 minus, and that is going to be 0 amps. So there are my initial conditions. Finally, we want final conditions as t goes to infinity. Again, the forcing function is a constant, so capacitors are going to look like open circuits, inductors will look like short circuits. So this has no current and this element has no voltage. If I do KVL around this loop, use KCL here to say that this has to be 6 amps, 6 amps going in, 6 amps coming out, no current through the capacitor. So V sub C at infinity is going to be the same as the voltage across this resistor by this KVL around this loop. So that's going to be 2 ohms times 6 amps, and that is again 12 volts. By KCL, this is 6 amps, so the inductor current is 6 amps. So I sub L at infinity is just 6 amps, and there's our final conditions. Now we can also use our final conditions to check our original differential equations. Let's go back and do that now. First, let's take a look at this equation. As t goes to infinity, again, the forcing function's a constant, so the derivatives go to 0. So 6 amps is equal to 0.5 times 0 plus I sub L. So I sub L of infinity is 6 amps, which agrees with our previous result. That's good. I can apply this line of reasoning to my original 2 differential equations. So as t goes to infinity in this differential equation, the forcing function is a constant, so derivatives will be 0. So I sub L at infinity is 6 amps. We keep coming out with the same result, so that's good. In this one, as t goes to infinity, minus V sub C plus 2I sub L, derivatives again go to 0, is equal to 0. So V sub C at infinity is equal to 2 times I sub L of infinity. I sub L of infinity is 6 amps, so this is 12 volts. That also agrees with our previous result.